Alright, so in this mini lesson we're going to be talking about logarithmic differentiation, which is a tactic used to derive exponential functions. That is, stuff that is kind of the form some number or some variable expression to some variable power. So here we have like 5 to the x, we have 2 to the x squared plus 2x plus 1. Notice that in all three of these cases you have a variable in the exponent. This differs from what we're used to deriving, which is like you have a variable in the base and some number to an exponent. Now here the roles are reversed. You have something else in the base and you have the variable in the exponent. So in short, logarithmic differentiation is used for exponential expressions. To be 100% clear, that means when you have variables in the exponent. Okay? There are special cases for when you have like e to the x and e to the x squared and such like that, but those you can also use logarithmic differentiation to handle that as well. So the idea is, well, we don't really have a way of, say, deriving this 5 to the x power. We have no rule for that. So what if we could somehow get that exponent out of the exponent somehow, like get it down in front somehow, some way, so that we don't have the x in the exponent anymore? How do we do that? Well, we might be able to leverage the properties of logarithms. So why don't we take a look at this first example here, just for starters. Let's take a look at f of x is equal to 5 to the x. What we're going to do is we're going to set this equal to y, because, I mean, a function gives you y values, right? Then what we're going to do is interesting. We're going to take logs of both sides. Now, the reason we do this is because when we have a log with an exponent on the inside of the log, the exponent gets moved down in front of the log, making this not an exponential anymore. So, simplifying this gives us x times the natural log of 5, which is equal to the natural log of y. All right? And the goal, of course, is finding y prime. That is, we want to find the derivative of this thing. So if you like, you can write f prime of x. Same thing. All right? So it's like, oh no, we just took a natural log of y. How do we handle that sort of circumstance? Well, we have the power of implicit differentiation. So that's what we're going to use in this case. So looking at this, let's take a look first at this guy. We have natural log of 5. That's just a number. So you can just pretend it's a number. So we have some number times x. We know how to derive that. So we're going to derive the right-hand side and the left-hand side. So deriving the left-hand side, we have some number times x. So that just leaves you with the natural log of 5, because the x goes away when you derived it. Now when we derive the right-hand side, how do you derive a natural log? Well, we know that the derivative of natural log is going to be 1 over whatever is on the inside. Okay? But then you have to multiply by the derivative of the inside because, well, y is a function in x. So we're going to multiply by y prime. All right? So what we have here is natural log of 5 is equal to 1 over y times y prime. Keep in mind the goal at all times. We wanted to find y prime. So how do we get that by itself? You multiply both sides by y. So that way the y here and the y here cancel each other, giving you y times natural log of 5 is equal to y prime. Okay, so we have y prime by itself, but it's not really helpful because we have a y in the left-hand side. We can replace that y, interestingly enough, with what we know y to be equal to. So since y is equal to 5 to the x, I can replace this y down here with 5 to the x. So I'll have 5 to the x times natural log of 5, and that's equal to y prime. That's it. Pretty neat. So we used implicit differentiation and log properties to get the exponent out of the exponent. We got the variables out of the exponent, so then we could derive it more easily. That's half the battle of calculus, is trying to put things into a form that is easy to work with. And this is just one tactic for doing that. It turns out this method is used no matter what your exponential expression is. It's going to be the same exact process. So let's illustrate exactly what we did here. What were the steps? So let me use green. Steps. So the first thing that we did was the red circled thing you see on the left. So we set function equal to y. Fn is my abbreviation for the word function. Our second step was take natural logs of both sides. The third step was derive both sides implicitly. And then the fourth step was solve for y prime. And then the fifth step, which you can kind of combine with the fourth step, is resub or resubstitute. Substitute y is equal to your function. So let's see here, where did these steps occur? Step 1 occurred right here. Step 2 occurred right here, where we took natural logs of both sides. We used log properties to simplify here in the third line, so that could be like a step 2.5 if you like. Sometimes you don't really need to do too much simplification, so I kind of omit it. But these are the 5 steps that are used every single time. All right, and then let's see here. Where did step 3 occur? We derive both sides implicitly in this line here. We also use that line to solve for y prime. So like these both combined are your step 4. And then your step 5 is here at the very bottom. Okay, so the set function equals y, take logs of both sides, use your log properties to simplify this thing to get the exponent out of the exponent, derive both sides implicitly, solve for y prime, resubstitute your function into the final result. So let's try a slightly different example. Let's go with the following. Let's use the following, the steps that we just developed. Let's go with f of x is equal to, let's do 2 to the, let's go with x squared plus 2x plus 1. Or let's go with x squared plus 2x. Keep it simple. Okay, now how do we handle this thing? Let's follow our steps. Step 1, set the function equal to y. Okay, so we have this lovely thing set up, ready to go. Now we take logs of both sides. So we take log of the left-hand side, giving us log of 2x squared plus 2x. This is equal to log of y. All right? Now we're going to use our log rules to simplify this. So notice that we have this exponent. We can bring that down in front because of properties of logarithms. So what this gives us is, in parentheses, x squared plus 2x times the natural log of 2, because we removed the exponent. The exponent got brought out in front, right? And then on the other side, we didn't do anything with that in terms of log properties, nor did we take derivatives. It looks like we took derivatives with this log property of bringing the exponent out in front, but it only looks like a derivative. It's not a derivative. All right, so now that we have this set up, what we're going to do is derive both sides. Notice that natural log of 2 is just a number. You can plug that into a calculator and it's going to give you a nasty decimal. So the only thing we really need to derive is this x squared plus 2x thing. The natural log of 2 will just come along for the ride. So when we derive this, this gives us 2x plus 2 times the natural log of 2. So the natural log just came along for the ride. Nothing unusual about that. We just derived the variable stuff. Then on the right-hand side, we derive this implicitly. So this gives us 1 over y times y prime, because the derivative of the inside of this log was y prime. Okay? All right, are we done yet? Not quite. The goal is to get y prime by itself. So we multiply both sides by y. So we can kill off the y on the right, the 1 over y. So now we have y prime by itself, and we have y prime is equal to natural log of 2. I'm kind of writing this in reverse. That's what we have here. But we also have to deal with this y here. How do we handle that? Well, step 5. Step 5 says resubstitute in our original function. That is, take this lovely thing and then plug it in for y. You take your 2 to the x squared plus 2x, and you substitute that in here at the front. And this is all multiplied. And that's your final answer. So it's kind of complicated looking, but the process is exactly the same for every single one of these problems. Okay, you just follow the steps that you have here, and you're bound to get the right answer. A lot of problems come in when you're trying to deal with the algebra or you're trying to handle the log rules. So if you're not familiar with some of these log rules, make sure you review them. There's going to be a link on this page to help you find, to help you practice those logs if you're not too familiar with those. And there'll be a table of logarithms also on this topics page, as well, like a table of log rules. So you can reference those. All right, so I guess that's the end of the lesson. A lot of these, all these problems work out exactly the same way, so I encourage you to try solving a few of these yourself. Check out the examples below and get cracking on this.